As we saw last time, subtle differences in the isotopic ratios found in once living tissue provide a record of an individual encounter with his physical environment. In addition, however, such ratios can record changes in the social environment of populations, such as shifts in food production and consumption. The history of agriculture is therefore written in the isotope ratios of carbon in human tissue. Carbon is the atom on which all life on Earth is based, and that's why we keep coming back to it, whether using carbon-14 for dating purposes, or, as we will today, the other two stable isotopes of carbon, carbon-13 and carbon-12, to understand the history of agriculture. Now, it's important to remember that carbon isotopes, like all isotopes, are chemically, but not physically, identical. All neutral carbon atoms have 6 electrons. Because all carbon atoms have 6 protons, that's what defines them as carbon. And the 6 electrons of carbon are arranged in a particular way, which makes it particularly versatile. 2 electrons in the first energy level, that's all the first energy level of any atom can obtain. 2 electrons in the first sublevel of the second level, and 2 electrons in the second sublevel of the second level. Those 2 outermost electrons are what make carbon such a willing partner to join up with other atoms to make a wide variety of molecules. And again, all carbon isotopes behave chemically exactly the same. But these 3 carbon isotopes, carbon-12, carbon-13, and carbon-14, have different masses. And the mass ratios are rather different. The ratio of 13 to 12 means that carbon-13 is 8% heavier, and carbon-14 to carbon-12 is 17% heavier. Now, recall that in any circumstance, the atoms, whether in a solid, vibrating next to each other, in a liquid, touching but sliding over each other, or in a gas, colliding with each other like billiard balls, the energy is shared amongst all of the atoms equally. With the energy shared equally, it means the heavier atoms move more slowly. You'll recall that the velocity is proportional to 1 over the square root of the mass. And so carbon-13 will be moving on average 4% more slowly than carbon-12, and carbon-14 about 8% more slowly. Remember the billiard balls, the bowling ball, and the ping pong ball on the pool table. The light ones go flying off, the heavy ones barely move, and the intermediate ones bounce around. So carbon-14 moves much more slowly, carbon-13 somewhat more slowly, than the dominant isotope carbon-12. In any chemical reaction, slower atoms are discriminated against. They just don't get there as fast, and so they don't have the opportunity to join up with other atoms to make molecules. Thus, the heavier isotopes will always be underrepresented in any chemical compound involving carbon. Since carbon-12 and carbon-13 are both stable, they never undergo radioactive decay, they form a permanent record of the chemical composition leading to the compounds in which they are found. Carbon-13 and carbon-12 ratio of a substance then reveals its chemical history, not just its origin, as we did by dating potassium and argon in rocks, for example, not just the conditions under which it was made, but its entire history, the processes it's gone through to reach the state in which we find it. The global carbon-13 to carbon-12 ratio is roughly 1.1 to 100. That is, there's 1.1 atoms of carbon-13 for every 100 atoms of carbon-12 in, for example, the carbon dioxide I breathe out of my mouth. We can easily measure this ratio with totally straightforward techniques to 1/100th of 1%, or 1 part in 10,000, and by using slightly more sophisticated techniques to a part in 100,000, or 1/1000th of 1%. Thus, even very subtle shifts in the carbon-13 to carbon-12 ratio can be easily measured and recorded. The standard value for this ratio is completely arbitrary, designated as that ratio found in a particular marine limestone fossil excavated from South Carolina in the 1950s. We have to have something as a standard. Every substance on Earth has a slightly different ratio of carbon-13 to carbon-12, and a long time ago, this particular fossil was designated as the standard ratio. The ratio found in all other substances, then, is compared to this and is expressed as a fractional deviation, a value we label as delta 13C, where delta is the Greek letter delta and always represents a change or a difference. We define this as the C13 to C12 ratio of whatever sample we're studying, minus the C13 to C12 ratio of the standard, this South Carolina fossil, divided by the C13 to C12 standard ratio. So it's a fractional change, measured in percent. A substance that's identical to the C13 to C12 ratio of the standard has a delta 13C of 0, because the two values in the numerator are equal. The range in all carbon-bearing substances we've ever found on Earth is from about plus 0.4% to minus 5%. That is, there are a few substances that have a slightly higher carbon-13 to carbon-12 ratio than this particular fossil, but most substances have a lower ratio of carbon-13 to carbon-12, all the way down to 5% lower. For example, air out in the country has a delta 13C value of about minus 0.7%. But air in Los Angeles has a value of minus 0.8%. Why is it lower? Because, unfortunately, those of you who have visited or lived there will know this, a non-trivial fraction of the Los Angeles air comes out of the tailpipes of cars on the famous Los Angeles freeways. Now, where does the carbon come from in the gasoline which these cars are burning? It comes from fossilized plants, oil, plants that were growing 100 million or 200 million years ago. And plants, as we shall see, discriminate in constructing their cellulose material against carbon-13. So the carbon-13 to carbon-12 ratio in gasoline is lower than the carbon-13 to carbon-12 ratio in air. Thus, in Los Angeles, there's a 0.1% difference from air in the country because a significant fraction of that air is contributed by car exhausts. On the floor of the Amazon rainforest, for example, the air has a delta 13C value of minus 1.55%, a huge discrepancy, as a consequence of all the carbon released from the rotting leaf litter on the floor of the rainforest, which, because it is plant material, is also deficient in carbon-13. Plants draw carbon into the food chain by absorbing it from the air as CO2, splitting off the O2, sending that back out again, fortunately for us, because that's what we breathe in, and using the carbon to make material in the process we call photosynthesis. The CO2 is drawn in from the air through tiny little openings in the underside of the leaves called stomata, which have little valves that can open and close more or less widely depending on conditions. Since the C13 O2 molecules move more slowly in the air than the C12 O2 molecules, fewer of them get to enter. It's like a crowd trying to enter a sporting event. The ones that are moving fast will get in before the ones that are moving more slowly. At each chemical step following their entry through the stomata, as complex molecules are built up in the photosynthetic process, again, because the carbon-13s that do get in are always moving more slowly, further discrimination occurs. There are three primary photosynthetic pathways. This has only been understood since the 1960s. It was originally thought that photosynthesis was photosynthesis, a particular chemical process which led from carbon dioxide in the air to the cellulose material that makes up a plant. It turns out that most plants, certainly most of those that live in temperate climates like the continental United States, are called C3 plants. Now don't confuse C3 for C12 or C13. The C stands for carbon in all cases, but 3 in this case stands for the number of carbon atoms that are linked together in the first step of the photosynthetic process. 3 carbons are linked in a little chain. Carbons are excellent at forming chains, which is why they are the basis of life. And most temperate plants and grasses and trees and shrubs and fruits and berries are C3 plants. It was discovered in the 1960s, however, that a few particular kinds of plants, in particular maize, the parent of corn, sugarcane, sorghum, and some salt-tolerant marsh grasses, began photosynthesis in a different way. Instead of linking 3 carbons together, they linked 4 carbons together. And so they are called C4 plants. But again, the C4 is not like C13. There couldn't be a C4 because carbon by definition has 6 protons, so its atomic mass must be at least 6. and in fact is typically either 12, 13, or 14. So 4 here, again, stands for the number of atoms linked together in the first step of the photosynthetic process. There's yet a third process called the CAM pathway, which is found primarily in succulents such as cacti. Now, to first approximation, most plants you encounter are C3 plants. The exceptions, again, are maize, corn, sugarcane, sorghum, and switchgrass in the US. C4 plants make up only about 1% of all plant species, and they're especially well adapted to drought, to high temperature, to high salt content, which is why they're found in some marsh grasses in salty water, and to low nitrogen and CO2 availability. Indeed, it is thought that C4 plants, this different pathway, evolved only recently, in the last few tens of millions of years, in response to a drop in atmospheric CO2 levels, which, as we will see when we discover the history of climate in the Earth's atmosphere, were considerably higher in the past, such that plants didn't require this extra route to photosynthesis. Now, the different chemical processes, linking 3 atoms together as opposed to linking 4 atoms together, lead to different levels of discrimination against carbon-13. There's greater discrimination in C3 plants because you only need 3 to get going. Whereas in C4, it's a little less picky because you have to wait around until you've got 4 carbon atoms all aligned to join up in the initial chain. The mean value of delta 13C for C3 plants is minus 2.65%. Again, these plants draw in air that's got a delta 13C value of minus 0.7%, and discriminate against the carbon-13 such that by the time the cellulose is formed, the value is minus 2.65%. The range for all C3 plants is about 0.6%. The mean value for delta 13C for C4 plants is minus 1.25%, less than half the discrimination that we see in C3 plants. Again, this process must be less picky because it needs to find 4 carbon atoms before it can get going. And the range here is only about 0.25%. The narrower range for the C4 plants probably just represents the fact that they're a much more recent evolutionary phenomenon, and they haven't had a chance to diversify as much as the C3 plants, which have been around for hundreds of millions of years. Now, since in our diets today we eat a mix of C3 and C4 plants, the isotope ratios from these plants is reflected in the carbon isotope ratios of our bones and flesh. But turning food plants into bones and muscle involves further chemical reactions, which again discriminate to a greater or lesser degree against carbon-13. In some cases, they even favor carbon-13 over carbon-12, the more slowly moving isotope. We call this level of further discrimination in a new set of chemical reactions the fractionation factor, which is the degree of change a particular set of reaction introduces into the delta 13C value. The fractionation factor for mammalian fat, for example, is roughly minus 0.3%. That is, an animal eating a diet exclusively of C4 plants would have fat with a delta 13C value of minus 1.25% for the C4 plants, minus another 0.3%, or minus 1.55% in total. The fractionation factor for bone collagen, the thing that's most likely to be left over if we find a skeleton, is actually positive. That is, the chemical process that creates bone actually favors the heavy isotope by a little over 0.5%. There's an aside here that's important. As you might imagine, the fractionation factor for carbon-14, which is even heavier than carbon-13, is even more severe. In fact, it's roughly twice as great. So if the fractionation factor for carbon-13 is something like 1.5%, the factor for carbon-14 will be 3%. When we're using carbon-14 for dating, we have to take this into account, because as you will recall, it's the ratio of carbon-14 to carbon-12, the radioactive isotope carbon-14, which is decaying away over time, with the stable isotope carbon-12 that tells us how old a substance is. What we do is use the C13 to C12 ratio in a bone as a proxy for the amount of fractionation there has been, and then apply that, updating it to the carbon-12 mass, such that it can be used to calculate directly the correction factor by which carbon-14 has been discriminated against, and thus changing the date. Ignoring this effect, which is about 3%, can yield a date for something that's a few thousand years old that's off by 250 years, far greater than the amount that the inherent carbon-14 dating technique can yield. So this is an important correction we have to keep in mind. The delta 13C value for bones can thus reveal the types of plants the organism ate. Since C12 and C13 are both stable, they never decay, this record lasts forever. A range of values is possible based on the mix of plants at the bottom of the food chain in that organism's diet. For example, it's not just if you're a hunter-gatherer and you're a vegetarian, so you're eating directly the plants that are either C3 or C4, or perhaps a mixture of the two, but the animals you eat who eat those plants also are going to reflect the C12 to C13 ratio of the mix of C3 and C4 plants they consume. So a direct measurement of diet is provided by this ratio and offers a powerful tool to reconstruct the history of human agriculture. Let's start with Native Americans of the Midwest, for example. Humans invaded North America nearly 15,000 years ago, and for thousands of years, those who migrated to the Ohio Valley subsisted for a long period of time exclusively on C3 plants and the animals that ate those plants, because only C3 plants were growing naturally in that area. Now recall that in 600 AD, the Anasazi, who we visited last time, were already cultivating corn, a derivative of the natural plant maize, which is found in the highlands of Mexico. It had already migrated through agriculture to the southwest of the US, but in the center of the US, corn was unknown. If we look at the bones of Native Americans from the Ohio Valley, we can measure their dates by standard carbon-14 dating. But we can also measure their diets by looking at the carbon-13 to carbon-12 ratio in their bones. And what we find is, for thousands of years, a diet based exclusively on C3 plants. Then, between about 1000 and 1200 AD, the delta 13C values start to climb. That is, they get less negative because C4 plants have evidently been introduced into their diet. This undoubtedly was a consequence of the introduction of maize agriculture. And by 1400 AD, their diet was nearly 70% derived from maize, or perhaps from turkeys or other animals, deer, that got into their maize patches and ate the maize, changing the composition of their flesh and bones as well. This technique, then, can be used to follow the spread of maize cultivation from its existence as a wild plant in the highlands of Mexico, 5,000 miles away, spreading across the US until by the time the Pilgrims arrived in New England, the Native Americans there were also cultivating this highly nutritious plant. This technique can provide invaluable complements to more traditional archaeological techniques in other areas of the world as well. In the Orinoco Valley in Venezuela, for example, it is known from standard archaeological techniques that there were large populous chieftains over 1,500 years ago. These were very hard to explain on the basis of the traditional anthropological view of a tropical forest system of manioc cultivation, that starchy root that's grown in South America, and hunter-gatherer activities. The anthropologist Anna Roosevelt challenged the standard interpretation that the populations grew only because they got even better at fishing and catching animals in the seasons in which they could do that, when the rivers weren't at flood stage, and even more intensive in their cultivation of manioc. She did this through standard techniques of anthropology by sifting through refuse piles and looking for remnants of food and food processing equipment. She concluded that over 1,000 years ago, large-scale bean and maize cultivation was already present in this area, but most anthropologists remained unconvinced. Thus, she decided to turn to the modern methods of carbon-13 to carbon-12 ratios to see if the bones of people of that time indicated a diet rich in any C4 plants. The first problem she had, however, was trying to figure out whether manioc, clearly the staple of their diet, was a C3 or a C4 plant, there was nothing in the literature which told her the answer. Since she was at the State University of New York in Binghamton, about 4 hours north of New York City, there was, at the time, in the supermarkets, no ready manioc available to advertise in the laboratory. And so the only source was to send her graduate students on an 8-hour round-trip drive to New York to go to a Puerto Rican market and bring back a manioc root so they could analyze it in the lab and determine whether it was a C3 or a C4 plant. Well, it turned out to be C3. But the measurements of the bones of the people of the Orinoco Valley implied a diet that was 80% C4 plants by as early as 400 AD, which is when the population in these chiefdoms peaked. This showed unequivocally that cultivation of maize had already reached Venezuela 1,600 years ago. Animal diets, of course, are also reflective of the delta 13C ratios in their bones of the diets that they eat. Since the mix of C3 and C4 plants depends on temperature and moisture, recall the C4 plants evolved in response to dry, salty, and hot conditions, it can be used as a proxy for climate change. The average value of delta 13C for the mix of vegetation on an African mountainside, for example, can be used to determine the altitude to within plus or minus 100 meters. The mix of C3 and C4 plants changes as you go from colder conditions to warmer conditions. Analysis of fossilized teeth from zebra in Lesotho show a change in the mix of grasses on the mountainsides in which they grazed from 85% C3 plants at the peak of the last ice age about 30,000 years ago to less than 40% C3 plants today, indicating this part of Africa was much wetter during cold periods, although, as we will see, other parts of Africa were drier during those times. Isotope ratios can also be used to actually monitor the purity of food. Honey you buy in the store that's typed pure clover honey is, of course, produced by bees who collect the raw ingredients, pollen, from clover or other C3 plants. That means the carbon 12 to carbon 13 ratio in the honey should be reflective of a C3 plant. Likewise, orange juice you buy in the store that says pure 100% not made from concentrate orange juice is also a C3 plant and therefore should have C3 carbon 13 to carbon 12 ratios. However, if the ratio is greater than minus 2%, the extreme of C3 plants, it suggests the product has been adulterated with corn syrup sweeteners, corn being, of course, a C4 plant and having a less negative C3-C4 ratio. Brandy, for example, should be purely from grapes, which are a C3 plant, and not boosted in alcohol content by adding grain alcohol, which is typically made from sorghum or corn, a C4 plant. There are also potential medical applications and drug testing scenarios which can use isotope ratios. For example, in 1997, in the Tour de France, this was called the Tour of Shame because of the initiation, something that has continued since, unfortunately, in doping amongst the athletes. The way this is done is to compare the C13 to C12 ratio of different substances in the body. For example, testosterone, something which athletes tend to take artificially, and cholesterol, which is produced with a natural C13 to C12 ratio reflective of the diet. Now, each bicyclist might have a different diet, therefore a different mix of C3 and C4 plants, or of the animals that eat C3 and C4 plants, and so each athlete would have a unique C13 to C12 ratio. But the cholesterol in that athlete's body would have the C13 to C12 ratio representative of his or her diet, whereas the testosterone, if taken as an injection, would have a different C13 to C12 ratio. This readily yields indication of illegal doping. Now, there are a number of other medical possibilities for this, and you know it's important when you type into Google words describing C13, C12 ratio in medicine, and the first 50 hits are for companies that are selling diagnostic equipment or tests for the consumer. For example, the C13O2 ratio that you breathe out can be read with laser spectroscopy, shining a laser beam in to excite the atoms, and provides a test for the common bacterium Helicobacter pylori, a bacterium which can infect the esophagus and the stomach, cause stomach ulcers, and even cancer. The presence for this can be tested by simply breathing out. And exhaled C13O2 can achieve an accuracy with this technique of 10 parts per million. That is a part per 100,000. Isotopes other than carbon can also be used to monitor the metabolic processes in the body. For example, the deuterium to hydrogen, that is heavy hydrogen to normal hydrogen in water, and the O18 to O16 ratio in CO2 and water can be used to test a basic metabolic rates in humans. And nitrogen 15 to nitrogen 14, two isotopes of nitrogen that exist naturally in the air, in your urine can test for liver function. Calcium 42 and calcium 44, the ratio of them in blood can be a measure of calcium retention and bone growth. One can also use experiments by manipulating isotope ratios and seeing how they're processed in the body or in a plant. Linseed oil labeled with deuterium, heavy hydrogen, was fed to mice in the 1930s and found that 1/3 of it was incorporated into fat tissue, the first metabolic study of how fats were incorporated into the body. Deuterium nitrogen 15, that is HN using the heavy form of nitrogen and the heavy form of hydrogen and the heavy form of nitrogen, double labeled leucine, was used to investigate protein metabolism. And H2O18, doubly labeled water, where you have the deuterium, heavy hydrogen, and the heavy oxygen, was used for daily energy expenditure, and calcium 48 to study in pregnant women how they metabolized calcium. It's not just carbon-13 and nitrogen-15, as I said, makes up about 1/3% of air, and nitrogen cycling in crop plants can yield great insights into the optimal use of nitrogen-based fertilizers for agriculture. If we label the nitrogen fertilizer with an excessive amount of nitrogen-15, not the natural amount it would get from the air, but an extra amount, we can trace the fate of that fertilizer through its whole life cycle. How much of it is taken up by the plant? How much of it remains in the soil? How much of it is just lost to the atmosphere? And how much of it, very importantly, is leached away in runoff waters? By studying the nitrogen in this way, we can come up with optimized fertilization techniques to minimize the amount that runs off into water supplies and damages their ecology, and maximize the amount that is taken up in plants. Everything alive absorbs atoms with specific isotope ratios reflecting their diets. All living things are what they eat. We've seen in this talk how this can be used in archaeological settings and also in modern-day medicine and in testing of food products. In particular, trees, another form of life, are what they eat. And trees hold a special place in our atomic reconstruction of history because they come in with a built-in, highly accurate clock, their annual growth rings. We'll see next time how we can reconstruct a history of climate over the past 12,000 years by studying the isotopic ratios in tree rings, as well as correct a flawed assumption regarding carbon-14 dating, all through the analysis of living and dead trees.